Okay, so let's look at what has really happened with carbon dioxide. You know, that is the principal result of the burning of fossil fuels. As you know, they will burn to form carbon dioxide or carbon dioxide in water if the fuel also has hydrogen like natural gas. So now, it's amazing that when you look at the trend from this is going back to about something like 1000 AD. Okay, so we are going back about 1100 years. Okay. This is what was the level of carbon dioxide in the atmosphere. Something like around 280 ppm or thereabouts. This is what it was, and it was quite constant. Okay, it was quite constant for a while. I mean, this could have been a natural aberration. That there was a decline for a while. Okay, and a marginal drop, not much. Okay, but then, around 18, actually, all, even before that, maybe around 1700, it started taking off. Okay, and this coincides with the birth of the Industrial Revolution. You know, as you know, that was the time when people realized that coal is a very powerful source of heat, and once that had been unleashed, okay, then of course all of industrial production took place, and then of course the steam engine, which was run on coal, all of that happened, and it was really the birth of the industrial revolution. But the industrial revolution, the real impact of it essentially started around 1850 or thereabouts, and you can see that there was a much sharper rise in carbon dioxide, from around 1850. And when we came to the 20th century, okay, so 19th century was still manageable, okay, but when we came to the 20th century and more, I will say the middle of the 20th century, so around 1950, or thereabouts, you can see what happened. This started shooting up, the carbon dioxide. Look at the trend, okay? And actually, when you look at it even more closely, what one sees is that it was really around 1980 or thereabouts, maybe 1980, 90, that it started becoming extremely steep, this curve. And today, in fact, you can see I just took the data from August 29th, so just 3 days ago, okay? And this is the level of carbon dioxide today, 411.84 ppm. Okay? So, can you imagine from 275, we have gone to 412 almost. I mean, it's just amazing. And if you look at the atmosphere is so huge, and there, to have made a difference of something like 130 ppm, is mind-boggling. What has happened, and the way actually these are measured, is that there are two places. One is that there is in the Arctic, these are places where, as such, it's all frozen ice, and basically what they can do is that, from the ice, they can get a fingerprint of how much carbon dioxide was there in the atmosphere. The reason is because what happens is that when water converts into ice, there is always some air that is entrapped. And from the composition of the entrapped air, you can actually tell how much carbon dioxide there was. And after 2013 or around that time, they've also been looking at a place in Hawaii, Mauna Loa, right? And they've been collecting data from both these places, and that's really the basis of being able to extrapolate or go back in time to the past. And also, of course, now there is no issue because you can directly monitor the carbon dioxide in the atmosphere. So we can see this. So and it says something very significant here, that CO2 had passed the 400 ppm level for the first time in the Arctic in the spring of 2012 and at Mauna Loa in 2013. Okay, so both locations, more or less, they got a kind of a convergence. So they knew that these numbers are right. Okay, and it says that this marks the fact that humans burning fossil fuels have caused global carbon dioxide concentrations to rise more than 120 parts per million since pre-industrial times. Now it is 130. Half of that rise has occurred since 1980. So out of that 120 from a point here, okay, half of that is effectively since 1980, which means just 40 years. Okay. And you can easily work that out, because if you for example draw a straight line here, and draw another straight line somewhere here, around 2080, what you can do is you can calculate the area under the curve, and from that you will come to know, how much is the incremental CO2 since 1980. Okay, so it's been phenomenal. Okay, and so if people are talking about CO2, there is a reason. Okay, that is just irrefutable. The data, it's right there. What is happening with CO2, and as we all know that CO2 is a greenhouse gas, so it actually absorbs radiation and it heats up the environment, the atmosphere. And because of that, when people are talking about global warming, okay, there's a reason, okay, that CO2 has undoubtedly increased in a spectacular way. Is it all clear to everyone? Everybody understood?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Now, let me ask you that suppose you had this data, 411.84 ppm of carbon dioxide. Okay. Can anyone work out, or all of you can work out, that how much does it mean in terms of the absolute amount of carbon dioxide that we have in our atmosphere? Can anyone say how you will calculate this number? And there are no assumptions. You just need to need some basic data which is all well known, and from that you can calculate it.
Using the atmospheric pressure, maybe.
Brilliant. Very good. Go a bit further. Now tell me. Yeah, very good. You are absolutely right. So what would I do? I know the atmospheric pressure. Say 1 kg per centimeter square.
Pressure is equal to force upon area, maybe. I'm not sure, sir.
I'm extremely happy. Okay. So now let me go through, okay, how you would calculate this. And I was just doing it out of curiosity, some of these things, okay, that how do you really calculate? Now, and the calculation is actually quite simple, okay, but you'll get a profound. You can imagine that if you tell someone that we can actually estimate the amount of carbon dioxide in the atmosphere, that's wonderful. What is atmospheric pressure? When I say 1 kg per centimeter square, it is that from the sea level, suppose I have a column 1 centimeter squared in width, okay, and suppose I take it all the way to the top of the atmosphere, the entire column, all the way from sea level and extending it to the outermost part, then obviously there is air, air all over, okay, and to some extent that air might be thin in some places, might be more in at the lower levels, but in total, if I were to see the total mass of that column of air, that mass is equal to 1 kg. So it is exerting, by its mass of 1 kg, the pressure which is 1.01 bar or 1 kg per centimeter square. Okay, so that is for 1 centimeter square. And now, knowing the radius of the Earth, okay, I can calculate the total surface area of Earth. If I now take 4 pi r square and I've got r, okay, you can calculate that this will be equal to 510.1 million kilometers square. So you can see that we have now calculated the Earth's surface area. So if I have 1 kg per centimeter square, as the total mass for an area of 1 centimeter squared of Earth, okay, then if I were to take this figure, right, from that I can actually get the total mass of the atmosphere. Okay, and what is that atmosphere? It's effectively roughly about 20% oxygen and 80% nitrogen, maybe a little here and there. Okay, so I can get that. Now I also have the data of ppm. So this ppm, 411.84 ppm of carbon dioxide, is actually a volume by volume figure. Now I can convert that into a weight by weight figure, because in this I need mass. That's effectively the weight is what we're talking about. So what you need to look at is carbon dioxide. What is the molecular weight of carbon dioxide?
44 grams.
44. Okay. And of oxygen and nitrogen?
Oxygen 32 and
32 and
14.
28.
28, sorry, for 28.
Okay, yeah. Because the N2. Huh? Okay. So, I can take the weighted average, like let's say 20% oxygen and 80% nitrogen. I can take 0.2 multiplied by 32 plus 0.8 multiplied by 28. You'll find a figure. Okay, that is actually the average, you can say, molecular weight, of the atmosphere. Okay, and that of your carbon dioxide is 44. So if I were to express it in weight percentage terms, or weight by weight, this 411.84, if I express it as percentage, will be 0.041184 volume by volume, and that will be equal to this multiplied by 44 divided by the average molecular weight of the atmosphere, and that figure will come to 0.06292. Can you calculate it out quickly?
Yes, sir. You get that answer.
This is the answer. You get that?
0.06292. Yes, sir.
Perfect. Okay. Very good. Okay. So now we know what is the weight percent of carbon dioxide in the atmosphere, and the total weight of the atmosphere is equal to 1 kg per centimeter squared multiplied by this area of the Earth's surface. Okay, so mass of carbon dioxide will be those two, this figure, okay, multiplied by this figure. What is this figure? 5.101 into 10 to the power 8 kilometers squared. Okay, all right. Why is it 10 to the power 8? Because this million, there is 10 to the power 6, and I've expressed this as 5.10. So 10 to the power 2 from there, and 10 to the power 6. So I'll get 5.101 into 10 to the power 8 kilometers squared. Okay, divided by. So because this term is expressed as centimeter squared, right? So this 1 kilometer is equal to 10 to the power minus 10. 1 kilometer squared is equal to, what is a kilometer? It's equal to 10 to the power 5 centimeter. 100 centimeters to a meter and 1000 meters to a kilometer. So that's 10 to the power 5. Okay. So 10 to the power 5 into 10 to the power 5 is minus 5 is, 10 to the power minus 10. Okay. So it will be 10 to the power minus 10 kilometers squared per centimeter squared. Okay. So your kilometer and kilometer will cancel out, and this 10 to the power minus 10, when it goes up, it will become 5.101 into 10 to the power 18 centimeter squared. Okay. So that's the surface of the Earth expressed in centimeter squared. Multiplied by, and so if I, instead of kg, suppose I express it in tons, that will be 10 to the power minus 3 ton per kg. Okay, multiplied by that 0.041184, or sorry, 0.06292%. I can write that as 6.292 into 10 to the power minus 4 kg per centimeter squared. Okay, all right. That's what I have. Okay, because that's the amount of this. So effectively, if you multiply this out, just see how much is the figure, whether you get this figure or not.
Yes, sir.
Coming? Okay.
Yes.
All right. So all of you have understood, and you can see that the atmosphere contains 3209 billion tons of carbon dioxide. Okay. So we have arrived at a profound number. Because you see, why it is important is that when we are saying it's coming because of burning of fuel, I mean, we have data on how much fuel is being burned, okay, year on year. How much coal, how much oil, how much natural gas, all that figure exists, okay. And I know the how much carbon it contains, those fuels. Okay? So I know that if I burn so much, how much carbon dioxide would be entering into the atmosphere every year. And there must be some relationship between that 411 ppm figure, and how much I'm burning. I mean, if I'm saying that it's correlated with the burning of fossil fuel, then the two must correlate. Okay. So effectively, you'll find, at least that you have now got the this figure that it is 3209 billion tons, okay, of carbon dioxide. Okay. So keep that in mind. I might ask you questions around these kinds of things in the exam, and you might have to do some simple calculation. You can see that I've not done any complicated calculations, nothing. It's just multiplication, division, and that kind of stuff. Okay, and see in just a few lines we have derived how much of CO2 there is in the atmosphere. Okay, good. All right. Now let us look at some of the facts in terms of carbon dioxide. And now I'm going a bit more into tonnages with respect to how much every country is actually emitting. Okay. Now, I took this from today's Times of India, so some of you would have already read it. Okay, air pollution cuts average lifespan in Maharashtra by 2.5 to 2.9 years. That's one. And India listed as most polluted country in the world today. Okay, this study was done by the Energy Policy Institute in University of Chicago. Okay, I mean these are data. I mean these are not things that anyone can refute, because these are just based on facts, based on the actual numbers. Of how much we burn, how much coal we consume, how much natural gas, how much oil, etc., etc. We know those. Okay, but the pollution is not just carbon dioxide. Don't forget that something like coal, will have a lot of impurities. It will have things like sulfur. We know, okay, there are nitrogen, okay, and these things when you burn, you will get SOx and NOx, emissions besides carbon dioxide. Sometimes, if during the process of combustion, some metals can volatilize and can go into the atmosphere. Okay, because you're talking about very high temperatures. Something like 1500 degrees centigrade or 1200 degrees centigrade at the time of combustion. And so there could be also metallic things which are going into the atmosphere, and obviously those would all be proportional to the amount of these fuels that we are burning. But you can see that we are in for big trouble. Okay, I mean, we are not even, you see, today we have not even catered to the requirements of all our citizens. Only the relatively affluent, the middle class and the upper middle class, these are the people who are splurging on energy and everything. People in rural areas, they are still struggling. Okay, imagine if they were to attain the standard of living as all of you, what would be the situation in terms of energy? So it's all great, we clap when, so much power is being generated. But we must remember the dark side. The dark side is that we will increasingly become more and more polluted as a country. And, we'll continue to be the most polluted country. Okay. Now, there are certain statistics, okay, which are important to note. And this is from 1960 till 2013. So the situation would be much worse now. Like China has grown by leaps and bounds in the last 8 years, and so has India. Okay, so these are 2013 figures, but the 2021 figures which I could not access will be obviously much higher, than these figures. But look how things have changed in the world. Who was the superpower? United States of America. Okay. Now, of course, I will say they are marginally lower than China in terms of superpower capability, and probably China would be the number one superpower today. Okay. Now, in 1960, okay, you can see this figure. This is in million tons is the unit, and these figures are in thousands. Okay, so we are talking about roughly 2,808. Okay, into 10 to the power 6, which means 2.8 billion tons. Okay, of carbon dioxide was being emitted by the United States of America in 1960. Okay, and who was the next biggest superpower then? Russia. And so this is Russia. Okay, Russia was nowhere near the United States in terms of this, and there were other reasons also. Okay, but United States and Russia, the Soviet Union was of course the sum of so many states, and this is Russia alone. Okay, now so what you can see is that the United States, in a matter of about say 50, now it is about 60 years, okay, has increased its emission of carbon dioxide by less than a factor of 2, close to about a factor of 2. So 2.8 or so and so, and this 5.2. This, if I express it as 5.2, it means 5.2 billion tons, because this 1000 and 10 to the power 6 will become 10 to the power 9. Look at China. Where was China? 780, okay, 780 million tons, okay, which means 0.78 billion tons, okay. And China in 2013 was 10 billion tons. Okay, you can imagine, right, what is going on, right? Means we are talking about a figure which is 12 to 13 times is the amount that they have increased their emission of carbon dioxide. Look at India. India, of course, started with a low base, so whereas China was 780, we were at about 120, 120,000, 120 million tons, okay. We have now grown to about 2.4 billion. Okay, you can see it looks less, but the fact of the matter is that we have actually grown 20 times, even more than China. That's because we started with a low base, but that has been the rate at which we have started emitting CO2. And I'm talking about 2013. In 2021 the situation would be much worse. Now, look at European countries. Look at Germany, look at UK. Interesting, their CO2 emissions have come down. Okay, why? Because all these countries, the European countries particularly, they kind of exited most of these very polluting manufacture, and it was all outsourced to China, India, and Brazil, and countries like that. Okay, and so what happened was that our pollution went up. They are looking like saints, but the truth is that it's just that they deflected the problem, right, from their country to our country. They were happy, we were also very happy. They were happy because their pollution has come down, but they moved on to very high-tech areas, the electronics industries, software industries, etc., where probably there was more money to be made and they were less polluting. Okay, and we went into these bulk production, steel, cement, this, that, pesticide, pharmaceuticals, highly polluting, dyes, okay, highly polluting industries. Okay, and and so that's what it is. Okay, and so there is a decline, and but what they forgot, these people, is that pollution does not stay within your country. So if let's say we are burning stuff and polluting a lot, fine, but that pollution is going to spread all over the world. And you can see what's happening in Europe. They're having some of their hottest weather. It's mind-boggling. In some places, the temperature is as high as places in Rajasthan during summer. I mean, that's the level at which things have worsened, and worsened all over the world. Okay? In fact, recently the US had a hurricane, Ida, and they were saying that when that Ida was traveling, up to Louisiana, the waters were so warm that when the hurricane was passing over the waters, uh, the amount of water that evaporated, into the hurricane, and that's the reason why it dumped so much of water on Louisiana. Okay, because it was so warm, and so it's going to suck in all that moisture, the hurricane, all right, and that's what it did, and it picked up wind speed. Wind speed was about 150 miles per hour, and so you have got a recipe for a disaster. Okay, so has everyone understood this graph? All clear?
Yes, sir.
Okay, okay.
Yes, sir.
Okay, now, and I hope you can see that, we are talking here. See, you can actually add up these figures. These are only figures for some of the countries, and this is 2013. If you go to 2021, I don't know what will be the figures. It will be much, much higher, maybe double. Okay, and so if you add up, you can see that now I'm coming to a figure of carbon dioxide in terms of billions of tons, which are being emitted, and this is data based on actual burning. Okay, and the calculation that we made, okay, was based on how much carbon dioxide is there in the atmosphere. Okay, but you start adding it all up. Okay, and this is for 1 year, and then if you take it for 60 years, the figures, you take the average figures, for each of these and work it out, you'll probably find that the incremental increase in the carbon dioxide, okay, in the atmosphere correlates quite well with this kind of an increase. Okay, and we will try and see that a bit more, in the next slide. Okay. Now I will pass this on to you. This is from the report prepared by the Intergovernmental Panel on Climate Change. In fact, at that time it used to be chaired by an Indian, R.K. Pachauri, from Delhi, and this Intergovernmental Panel also won the Nobel Prize, for their work, and I think that they tried to prepare a very exhaustive report and bring out, some of the serious concerns. Okay. Now, around the time that they were preparing this report, in 1999, the figure was about 367 ppm CO2. You can see how much it has gone up, in another 20 years. Okay. So that's why this figure, because this report was prepared some time back. Okay. Now, and it says what I already told you, that there was virtually no change in carbon dioxide concentration in the atmosphere for about, the past, as they say, 420,000 years. Okay, and what has happened in the last 100 years or 50 years has been absolutely phenomenal. And they say over here, about 3/4 of these emissions are due to fossil fuel burning. Okay, and they are now making a very categorical statement that that increase was due to burning of fossil fuel. Okay, now you can actually calculate that if and they have estimated the carbon, that if I take 1 petagram of carbon. Okay, petagram means 10 to the power 15 grams. Okay, now 1 petagram of carbon has an atomic weight of 12. If I convert that to CO2, that which is 44, that will be equivalent to 3.7 billion tons. Okay, so because it will be 44 divided by 12 into 10 to the power 15. Okay, and 10 to the power 15 grams is equal to 10 to the power 6 grams in 1 ton and multiplied by 10 to the power 9. So 10 to the power 15 gram is equivalent to 1 billion tons. Okay, and so 1 billion tons of carbon is equal to 3.7 billion tons of carbon dioxide. Okay, and this was the emission per year. Okay, during 1980 to 1989, right? And from 1990 to 99 was this, and you can work out for 2000 to 2020. Okay, obviously it will be higher than this figure. Let's assume that it will be a figure of say about close to about 8, if I assume. Okay, so now see, this is the figure per year. How many picograms per year? Okay, and I'm covering the figure from 1980 to 1989. So it will be 5.4 multiplied by 3.7 billion tons is equal to 1 petagram. Okay, multiplied by 10 years. Okay, so that is the total amount of CO2 for a 10-year period from 1980 to 89. And then you add to that the figure from 90 to 99, and then from 2000 to 2020. Is it clear? How is it so high?
For the 20 years, the last part, what you have to multiply, it is 3.7 into 7.5 into 20.
Bas, that's it. And that should be a figure of 555.
Yes, so it comes up to 987.9 total.
Total, isn't it?
Yeah.
Huh?
Yeah. Yes, sir.
Right.
Yes, sir.
So 987, which is about 1,000. Yes, sir.
Yes, sir.
Okay, so you are talking about 1,000 billion tons. Correct?
Yes. Yes, sir.
And now, if you see this figure, 3209 billion tons, okay, you can see that from 1980, we are talking about roughly 30%, okay, has basically come from 1980. You understood?
Sir,
So
could
the
you repeat?
total CO2 in the atmosphere, 30% of that has come since 1980. Okay, is that clear? Everybody has understood the calculations?
Yes, sir.
Okay. And I hope now you can see the importance of calculating something. I can always talk in a qualitative way. This is happening, that is happening. And you can see that it's for real. Okay, the things are actually adding up. Okay. Now, even though, we have this data, all right, people were still trying to be 100% sure that, how are we absolutely sure that it is due to burning of fossil fuel, although it seemed reasonably evident. Okay. But let me tell you, the other lines of evidence, which were generated, okay, which basically makes it irrefutable. Now, the first is that what is a fossil fuel? What do you mean by fossil fuel?
It is basically biomass which has converted into more calorific form due to pressure and temperature over millions of years.
Over millions of years. So there's an element of time, right? Now, what happens is that, do you know what are the isotopes of carbon?
C14 and C12.
There is one more, C13.
C13.
Okay. C14, C13, C12. And out of this, C14, as you know, is radioactive and it is used for carbon dating, right? So you can find out how old something is by doing carbon dating. Everybody knows that?
Yes, sir.
Yeah.
Yes,
So
sir.
what happens is that our atmosphere has not only carbon 12, but it also has carbon 13 and carbon 14. Very little carbon 13, some amount of carbon 14. And I tell you where it's coming from. Okay. Now, carbon 14 is radioactive. But because it's a fossil fuel, what is the half-life of carbon 14? Well, it is in excess of 5,000 years. Okay, it's around between 5,000 and 6,000 years. Okay, so which means that every 5,000 years, okay, if I have X amount of carbon 14, after 5,000 years it will become X by 2, right? Because half-life is that, and so 50% has radioactively decayed. So, and after another 5,000 years, it will become 1/4. Okay, and it will go on. So you can imagine that over millions of years, there will be no carbon 14 left in your fuel. So if you have got a fossil fuel will likely not have any carbon 14. Okay, whereas if I take a live plant, you pick up a plant from your garden and do a dating, you will find there is carbon 12, there is carbon 14, there is carbon 13. Okay, so what they found is that in the atmosphere, just as the carbon dioxide was going up, what they found is that the carbon 14 percentage in the atmosphere was coming down. Okay, and it tallied exactly with what you would expect if there was no carbon 14 in the fossil fuel. You understood? Okay, so people knew that yes, in that case, there must be a role of fossil fuel in this whole thing. The second thing was that, tell me one thing, when you burn carbon or burn up fuel, what else happens? What else gets consumed? And what gets formed?
Oxygen, sir.
Oxygen, right? So oxygen gets consumed, and what will form is carbon dioxide and water. Okay, so what they found is that the atmospheric oxygen, right? The atmospheric oxygen is declining at a rate comparable with fossil fuel emissions of CO2. So the two are going hand in hand. So if today, we are having a lot of problems, it is partly because one is that carbon dioxide is increased, and the other is that oxygen levels are coming down, so people are going to have problem breathing. Okay, and the two were, tallying reasonably. Second, as I told you, the isotopic signature very clearly indicated that it is fossil fuel because C14 had come down. Okay. The third is that it's very interesting. In our world, most of the anthropogenic activities are actually happening in the northern hemisphere. There is very little activity in the southern hemisphere. Okay, and what they found is that the increase of CO2 is higher in the northern hemisphere than it is in the southern hemisphere. Okay, and so they could correlate that also with basically the burning of fossil fuel, which was a consequence of higher anthropogenic activity. And so these were very, very interesting. Okay, now what I told you up till now is all related to the atmosphere. Okay, but don't forget that our world basically also has land and it has water. And in terms of absolute mass, the mass of atmosphere is very limited. Okay, it's very small. Okay, so we will also start discussing about what happens in the water and what happens in the land. That I told you about carbon 14. it's important that you understand how exactly carbon 14 gets formed in the atmosphere, and carbon 14 in that sense is renewable resource. It continuously keeps forming. What happens is that our Earth, our stratosphere is continuously being bombarded, okay, by cosmic rays, okay, and they are very high energy radiation, and these basically form a certain number of neutrons, okay, neutrons. Now, these neutrons effectively react with nitrogen, okay, and what happens is that one neutron getting converted into a proton, it comes out from the nucleus, okay, and because one neutron has effectively got converted into something positive, so the atomic number of nitrogen reduces by 1. So from nitrogen 7, which is the atomic number of nitrogen, it goes to 6. All right. So effectively, you end up forming carbon 14. Okay, with an atomic number of 6, starting from an atomic number of 7, that extra positive charge having been taken away in the form of a proton. All right. So that's how continuously carbon 14 is forming. Okay, and the carbon 14, as I told you, once it is in a fossil fuel, there is only decay, because it's not a live plant or animal anymore. It is just decaying, and all of the carbon 14 will steadily decay, and this is the way in which it decays. Okay, carbon 14 basically emits a beta radiation, okay, and now I'm emitting a negative charge, so effectively you can think of it as a neutron getting converted into a proton, in this process, and don't worry about it. These are it's known as an electron antineutrino, okay. This also is a particle that gets emitted, okay, but effectively because of this, the carbon 14 decays. And this is a spontaneous process, and the half-life is about 5,700 years. Okay, so that's how they know if it's a live plant. A live plant will always have a balance of the atmospheric carbon dioxide, because the plant is taking in carbon dioxide from the atmosphere. And so it will basically again that will be the footprint. So, for example, it's interesting. Suppose you're talking about biofuel, okay, and let's take ethanol, okay. And what is ethanol made from?
Molasses.
Right, from fermentation of molasses, or and so it's a plant product, okay, and so that ethanol will have the same kind of carbon 12, carbon 14 ratios. There are little changes. I'll explain that later on when I'm covering photosynthesis. Okay, but whereas the fossil fuel will not. It went like that, but after that it continuously kept decaying. Now it's important, like suppose let's say a government says that I will give a subsidy for putting ethanol in your car, 20% subsidy, biofuel, right? And we also know there are ways of, for example, making ethanol from ethylene, which is derived from fossil source. Okay, so if some guy, a crook, makes ethanol that way and tries to pass it off as biofuel, you can catch the guy by kind of estimating the carbon 14 to carbon 12 ratio, in his or her fuel compared to an authentic ethanol made from, let's say, molasses, and you'll come to know. Okay, so these are also very, very important, in terms of being able to characterize what really is the origin of a biofuel. Is it a true origin? Is it a genuine biofuel, or is it a fake biofuel? Okay, you'll be able to know. In fact, the same thing is now happening. Today people tell you that they are making green plastic, where, for example, polyethylene. They will tell you that we are selling green polyethylene. What is green polyethylene? From ethanol. If you do a dehydration, you'll get ethylene. Okay, then you polymerize it, you'll get polyethylene. Just a second. If somebody is playing mischief, you'll be able to catch them by this kind of a isotope ratio study. Okay, now let me. So we have seen that there is a burning of fossil fuel, which is contributed very substantially to CO2, and it is something that is happening every year. Okay, it's continuously happening. Okay, but there are also other situations which can suddenly increase the carbon dioxide in the atmosphere. Okay, one of course could be that burning of forest. Suddenly the forest catches fire. And there have been massive forest fires. Okay, and so that also can lead to a surge in carbon dioxide. There is also something known as an El Nino effect. Has anyone heard of El Nino? Have you heard the term?
Yes, sir. It is a kind of a heat wave that was formed above North America towards the
Right,
Pacific side.
right. Very good. Okay. Excellent. Okay. So let's try and understand, what happens in El Nino years. Now, what was found, is that there are, in our Earth, there are two kinds of winds, which are known as trade winds. Okay, one is basically blowing from the in the northern hemisphere, from the northeast to the equator. Okay, and there is also one in the southern hemisphere. Okay, and these are known as trade winds. Okay, now trade winds are typically quite constant, but in what are known as El Nino years, these winds tend to weaken a lot. Okay, now let's try and understand what happens because of these trade winds. Okay. Maybe it will be a bit easier if I go to the next slide and try to explain it. Now, and by the way, this image was actually taken by NASA from one of their satellites, which proved the existence of the El Nino effect. Okay, so what typically happens is that waters from the Pacific Ocean, okay, they start moving from the southern Pacific. They start moving westwards. Okay, and these waters are typically quite cool. Okay, now what happens then is that these waters, as the wind is blowing, the waters will get even cooler. Why? Because of evaporation. It is taking up a lot of latent heat. And so the waters start getting cooler. Okay, and the water then moves towards the towards what is known as towards places like Japan, New Guinea, those kinds of areas. The water starts moving, and the waters which are there, in those areas typically tend to be much warmer. Okay, those waters. Okay, and whereas the waters in the Eastern Pacific become quite cool. They become cooler. And there is a simultaneous effect which is known as upwelling. I'll explain what that is. But the winds are also pushing water. And the sum and substance is that fairly warm water collects, in one area, and the Eastern Pacific tends to be quite cool. Okay. Now, in El Nino years, when the winds are low, okay, then what happens is the waters which had come, the warmer waters which had collected, they again start spreading into the entire Pacific Ocean. Okay, and so the entire Pacific Ocean starts heating up. Okay, and because of the heating up, it becomes warmer. Okay, so obviously that when something is warm, the solubility of a gas will be less. Okay, solubility of a gas is typically higher at lower temperatures, so it starts releasing carbon dioxide into the atmosphere. And obviously, because it has released carbon dioxide into the atmosphere, the water over there will now have less CO2, but the atmosphere will have more CO2. And this is the picture that they took. This white part, is all that warmer water. The entire Pacific had warmed up, because of the slowing down of these trade winds. Okay. So, and what they found, is that the as you can see in the Pacific, in the place where normally the waters are meant to be cool, but the whole thing has warmed up. What happened was they found that the carbon dioxide in the water was less; it had reduced, but it was countered by a rise in the atmospheric CO2. So that is really known as the El Nino effect. And so this will be superimposed on the burning of fossil fuel. Sometimes it will be more, sometimes it will be less. So if you just monitor CO2 at a particular year, you may not necessarily get the right result. Okay, so you'll have to monitor it over extended periods to even out the effects due to things like El Nino. Is that clear? Has everyone understood?
Yes, sir.
Sir, in Western Pacific, how water gets warm up?
Because you are moving more towards the equator. Okay, so because you're moving towards the equator, the water is warmer in that area. Okay, and the winds from the eastern area are pushing the water towards that equator. Okay, the winds are like sweeping the water, and the water is heating up because you are going closer to the equator. Okay.
Okay, sir. Okay, sir.
And when the wind stops, or slows down, again that hot water starts drifting towards the east. Okay. Now, along with that, there is this phenomenon. Okay. So effectively, you can see that this is the surface winds. Okay. The winds are basically, in any case, if I take water, okay, the top surface of the ocean always has a higher temperature than the bottom. As you go towards the bottom, the temperature of the water becomes cooler and cooler. And the winds are carrying this water. In any case, it's a bit warmer than the rest of the water. Okay, so what is being blown towards the equator is the relatively warmer water. Okay, and when it is reaching the equator, of course, because it is near the equator, it is heating up even further. Okay, now because the water is moving, from the eastern Pacific towards the west. Okay, so what will happen is that there will be a compensation of water, from the bottom, which will start traveling up. Okay, and so that is what is known as upwelling. So it basically starts filling the gap. Water is going from the top, and water from the bottom is now moving towards the top. Okay, And this water, which is at the bottom of the ocean, is typically colder, and this water is also much more nutritious. And typically, I remember, we were doing some work with Mauritius at one time, and they had shown me some of their analysis of water from 2 kilometers deep. And you find if the phosphate levels, etc., in the water are much higher. And so, if you want to, for example, grow biomass, in the sea, and if you can get hold of this water, which is this slightly cooler and more nutrient-rich water, you can have much better productivity. Okay, it happens, of course, naturally through the process of upwelling. Okay, but let me tell you that there are other technologies which people have been contemplating, particularly for taking out fuel from the bottom, and where in the process, what will happen is that for example, if for example I'm trying to do some kind of an distillation process from seawater, okay, say I'm trying to do desalination, and I obviously will need to condense that water. People actually pump very cold water from the bottom, and put it to the top, and then it becomes like a condenser, and it condenses that distilled water, okay, evaporated water, and that water now can become available for with higher nutrient content, and it might be actually good for actually growing some biomass in the sea, things like seaweed, etc. Okay, so this is the entire process of El Nino, and the consequences which are upwelling, which can be quite positive in certain respects in terms of bringing nutrients from the bottom of the sea up to the top. Okay, now let us look at the various parts. We have talked about the atmosphere, but you have atmosphere, then you have land, and then you have ocean. Okay, that's what you have. Okay, now the things within the square boxes, these boxes, okay, are basically the figures in petagram, which we call 10 to the power 15 gram. So atmosphere, you can see, has 730 petagram, okay, of carbon. This is carbon, okay, and so just like we did last time, 730 multiplied by 10 to the power 15, okay, multiplied by 3.7 to convert it into CO2, I get 2701 into 10 to the power 15 gram, which is equal to 2701 billion tons. So you can see that this figure is quite consistent with the earlier figure in terms of ppm of CO2. Okay, so it's quite consistent. Now, what this thing also tells you is that if you look at the total mass balance, for carbon in our world, okay, actually the amount in the atmosphere is relatively less, okay, and you can see that. The amount on land, okay, due to forests, etc., is also relatively high, but not that high. If you take the amount in the soil plus in the plants, you're talking about roughly about 3 times the figure as in the atmosphere. 730 and 1500 plus 500, we're talking about 2000, so roughly about a factor of 3. The real carbon sink is the ocean. Okay, this is where large amounts of carbon actually exist. Now, this carbon is what do you think is this carbon? What is the form of this carbon?
Calcium carbonate.
Very good. Anything else?
Sir, other carbonate salts like magnesium carbonate.
Well, I mean, there are dissolved carbonates, right? you know that you can have a carbonate bicarbonate buffer, right? And so, you know, our seawater always has, you know, this kind of a buffering action due to the presence of carbonate bicarbonate buffer. Okay. And you know, and so what happens with a buffer is that, you know, what is a buffer? I mean, even if I add some acid or a alkali to it, the pH doesn't change much, right? Remains reasonably constant, okay, because of the buffer. And so what happens is that, you know, carbon dioxide from the atmosphere tends to move to the ocean because of this buffering activity of the ocean, you know, and so, you know, there is this kind of a flux. These figures, which are on the sides of these arrows, are what is known as the flux. You know, how much picogram of carbon per year actually moved in different directions. It could move in this direction, and some of it could also move in this direction. Like, as we said, if I have El Nino years, you know, what will happen is carbon dioxide, which is in the water, because it's the warming effect, can move up, you know. And in some other times, carbon dioxide can move into the water. Okay, so there is a kind of a two-way movement of things, you know, and this is known as a flux. You know, this is typically, you know, the kind of an exchange of CO2 that happens between the atmosphere and the ocean. Okay, but of course, the absolute amount of carbon in the ocean is much higher. It's about 50 times that in the atmosphere, you know, and roughly about 15 times that or 20 times that on land. Okay, now similarly, what you will have is that we know, after all, what do plants do? Plants will do photosynthesis, right? So they will take carbon dioxide from the atmosphere and they will do photosynthesis. Similarly, if you have got vegetation in water, you know, those will also take up CO2, you know, from the oceans, you know, and do photosynthesis, and the CO2 will again then move into the ocean because there is a consumption taking place in the water. Okay. Now, this thing, there is a flux which is typically about roughly about 120 petagram. Okay, so you've got some idea, you know, of what is the exchange of carbon dioxide between the atmosphere and the land, and between the ocean and the atmosphere, and also, you know, there will be some amount, you know, of migration between the land and the water. Okay, and so, you know, one of you mentioned about carbonates. Okay, those are effects, you know, due to weathering effects, which typically will occur in a very long time scale. So there are some things which happen over a short time scale, like these are all short time scales. But things like weathering, you know, carbonation, okay, these occur over a very, very long time scale. Fossil fuel, our fossil fuels are occurring over a very long time scale. So these things, you know, these dashes represent very long time scale. Suddenly, if you have a volcano, you know, where of course massive amounts of energy get released, where does it get released from? It gets released because there are things in the geological reservoirs, you know, which are basically reacting and creating tremendous heat, you know, and you have a volcano and things are spewing out, you know, over here. Okay, so these are of course very, very long time scale things, the carbonate formation and the fossil fuel formation. But this overall gives you an idea about what is the kind of carbon reservoirs in the atmosphere, in the soil and plants, and in the ocean and deep down. Okay, this is the deep down, which is below the ocean. the geological reservoirs that we have. Okay. Is everybody clear? All understood?
Yes, sir.
Okay.
Yes, sir.
Okay. Now let's look at uh, the human perturbations. Okay, and what that effectively does. Okay. Now, if you see that there has been a lot of burning of fossil fuel, okay, and typically it is 5.3 petagram, so multiply that by 3.7, you'll see that it is roughly about 20 billion tons of CO2. Okay, now there is another, which is mentioned here, although the figure comparatively is much less, which is about 0.1 petagram. Can anyone tell me why cement production has been put? How does cement production contribute to CO2 in the atmosphere?
So calcium oxide is needed, and so while
Crushing of
decomposition
limestone.
of calcium carbonate, CO2 is released.
Excellent, excellent. One of the constituents in making cement is limestone, and when you burn it and you form calcium oxide, and that then reacts with silica and other things to form calcium silicates, those are our cementitious materials, and quite a bit of carbon dioxide is released into the atmosphere. Okay, uh, and obviously, the more you have urbanization, the more buildings, bridges, this, that, the requirement of cement is going up very, very steeply. This is a global figure. You know, in our country, in China, the construction activity has been massive. So our contributions towards this could be proportionately much higher. Also because we have got one of the highest populations. Everybody needs a house, some place to stay. So there is a very, very large amount of CO2 that is coming from urbanization due to things like infrastructure development and building houses, etc. Now, all of these are one-way traffic. It's not really one-way. These are basically contributing to atmospheric CO2. Okay. Now, the land in turn is taking up some of the CO2 from what? Basically from things like photosynthesis. Okay. So there is a reverse migration of CO2 into the land. Okay, because of uptake by plants, soil, etc. Soil microbes, things like that. Okay. Now, on top of that, there is another very, very significant thing that is happening, and that is probably one of the biggest concerns today. That every year, what we are finding is that there is increasing desertification. That is, more of land which once upon a time used to have forests, where there was greenery, and it has become absolutely like a desert. And that is happening. The second is a lot of forest land has been cut down, and why? Because people are trying to make space to build more houses as our population is growing, So you're cutting down on forests, and they can, in fact, not only will the photosynthesis stop, but what also happens is many times, those things which are cut, they're burned, okay, and so it releases CO2, okay, or it can just rot in the land, and that CO2 will come out, okay, as it putrefies. Okay, so either it could be actually combustion, or it could be a period over time, and not only that, sometimes these things can not only form CO2, but quite a bit of methane, can get released. Okay, so Now, so remember the fluxes towards the atmosphere and the flux away from the atmosphere. Now, in the ocean, what has been found is that although we talked about this equilibrium between the atmosphere and the ocean, but there is a net uptake of about 1.9 petagram, of carbon in the ocean. Okay, and this is mercifully saving us. This obviously you can imagine that the more of it I can soak up in my ocean, the better it is, because it will reduce the atmospheric CO2. The more number of trees, etc., I have, it will soak up more CO2. So those will happen. But if what is happening is that although the sea is a buffer and it can absorb CO2, but there is a capacity. There is only so much of CO2 that it can take up. Once it ceases to have the buffering activity, you're finished. You cannot convert the carbon dioxide, into the bicarbonates and carbonates. How will you do it? It's lost its buffering capacity. Okay, so and it could be calamitous, because suddenly one day you might find, it's become unbearably hot. The other thing is that because the waters have become hotter, the ocean temperatures have gone up by something like 1.5 degrees to 2 degrees centigrade. Okay, so we know that the solubility of CO2 is less in a hot condition. So steadily, the ability of the ocean to take up this CO2 is going down. Okay, but even so, even if I take today's point in time, okay, what do I find? That 5.4 petagram went into the atmosphere from the burning, okay, and then 1.7 petatons came from land use change, because forests are being cut down, and forests are burning. Okay, so these together becomes 5.4 plus 1.7, 6.4, 7.1. Okay, 7.1 petaton net flux towards the atmosphere. How much came out from the atmosphere? 1.9 and 1.9, 3.8. Okay, so what has happened? Okay, what has happened is that between 3 and 4 petatons of CO2 is building up in the atmosphere every year. And that is how the incremental increase of CO2, to 400 ppm is happening, because the ability of the land and the ocean to mop up what you burn is simply not adequate. It just doesn't happen. So, unless there is a massive change somewhere here or here or here, this situation will continue. Okay, things will get worse and worse. Now, let us look a little more at the ocean. I'm not going to go into too much of detail, and in any case, I will be passing on the report, But as I told you, that CO2 basically in the ocean exists as dissolved CO2, carbonate, bicarbonate. The more alkaline is your water, the more will be the ability to take up CO2. And carbonate will become bicarbonate. Okay. But as I said, as the waters are becoming more and more acidic, you are going to be in big trouble because this is not going to be able to buffer that much of CO2. Another concern is that we have just expressed it based on CO2. You know? But as I told you, when you burn fossil fuels, there are acidic vapors, SOx, NOx. They will find their way into the water and they will acidify the water. So our waters will possibly be turning more and more acidic. And because of that, the buffering capacity is going to get worse and worse. Okay. Now, there are processes, after that, which are very interesting, okay, which take place. Those carbonate, bicarbonate, etc. Finally, they get fixed deep below into things like calcium carbonate. Okay, and so that is the fixing that we all pray for, hoping that it happens. But what we are today doing is fixing less and unfixing it more by taking out the calcium carbonate and converting it into cement. So one thing that you must remember is that while there are lots of projects, and I've shared some with you, where people talk about that you ask people, what are you working on? Or they'll say, oh, I'm trying to, fix CO2. And people are doing a huge amount of research on that, how to take CO2 and fix it. But, the wisest thing to do will be not to unfix what nature has taken millions of years to fix. See if you can find better solutions to that. Don't try to unfix something which was fixed over millions of years and then say, hey, I'm working on trying to fix CO2. It's just not going to work. Okay. I mean, unless, of course, you are able to completely reverse the desertification process, all the land use change, and generate biomass, create a huge sink for CO2 by having massive amounts of greenery. That's one way in which it will happen. There's also another thing that you need to know, that in the ocean, there is something known as the divide between what is known as a thermocline and an isocline, and effectively this is a very abrupt change in temperature, which takes place between a thermocline and a lysocline, and many of the geological processes, etc., will happen in deep down, in the lysocline. Okay, but there can also be very dramatic changes in the behavior of calcium carbonate, etc., in the lysocline. It can decompose also faster, but I don't want you to go into all the details of it. But all I want you to know is that there is a huge number of competing processes which take place in the ocean. Okay, and what we see is the net result of all of those competing processes. And anytime someone tells you something, try to think about the complexity of these equilibria, and what it all means. Okay, so just keep that in mind. Okay, and anyway, I think I'll skip this, and this is the other part, which is when so much of biomass it starts losing its ability to divide and grow, because they have gone dead or whatever, and those things will ultimately release CO2 into the atmosphere. And we will discuss this a bit when we are talking about hydropower. And because while hydropower has many great things about it, there are some devastating consequences of hydropower. We will discuss it at that point. Okay. Uh, but broadly, have you understood the equilibrium? Is it clear?
Yes, sir.
Okay. Okay.
Yes, sir.
All right. So if we can now summarize, the responses of the carbon cycle to changing CO2 concentrations, let me read it out. Uptake of anthropogenic CO2 by the ocean is primarily governed by ocean circulation and carbonate chemistry. So long as atmospheric CO2 concentration is increasing, there is net uptake of carbon by the ocean, driven by the atmosphere-ocean difference in partial pressures of CO2. The fraction of anthropogenic CO2 that is taken up by the ocean declines with increasing CO2 concentration due to reduced buffer capacity of the carbonate system. Because more CO2 has gone down into the oceans, and the carbonate is getting converted into bicarbonate, and slowly the bicarbonate will ultimately release CO2. As it gets more and more acidic, because don't forget, carbon dioxide is an acidic oxide. Okay, don't forget that. All right. So just keep that in mind. The fraction taken up by the ocean also declines with the rate of increase of atmospheric CO2, because the rate of mixing between deep water and surface water limits CO2 uptake. Now, this is again very, very interesting. You see, what did we talk about, when we were talking about upwelling? Deeper waters are cold, and we know that when waters are cooler, their density is higher. I'm not talking about reaching the point of ice formation. I'm talking about temperatures in the range of 15 to 30 degrees centigrade or 10 to 30 degrees centigrade. So these waters are cool and they're more dense. So what happens is that these waters are warmer. Now, because they are warmer, warm water will always float over denser water. And so there is no convective process which can lead to a mixing. Okay, this is denser and at the bottom, and this is lighter and at the top. Okay, because the temperature is higher. So, although there would have been a higher capacity, maybe for the oceans to mop up more carbon dioxide, this restricts it. The temperature difference between the lower part of the ocean and the upper part of the ocean. And the very top part will be the hottest. So it will remain there, and unless you have very strong trade winds, and upwelling processes will bring cold water to the top, which can then absorb a lot of CO2, you're stuck because of this. Is everyone clear about this? Okay, the density effects?
Yes, sir.
Okay. And the other very interesting thing is that, see, increasing atmospheric CO2 has no significant fertilization effect on marine biological productivity. Okay, so like for example, a lot of work has been done as far as land is concerned, and what has been found is that the rate of photosynthesis increases as the carbon dioxide in the atmosphere goes up. Common sense will tell you that yes, that is going to happen, and it has been predicted that even if the atmosphere were to, let's say the CO2 increases to something like 800 ppm, you can actually still do photosynthesis, and you can actually enhance the rate of photosynthesis. So there will be a good amount of reverse migration, of CO2. Okay, but beyond this point, the plants become toxic to CO2. And at that point, the plants might die. if you try to increase the CO2 beyond that point. Okay, so there is a nervousness also on that count, that can it affect the fundamental nature of photosynthesis? You know, and could such high levels of CO2 at some point make it toxic to plants? So this is something that we always have to be very worried about. And sometimes it is not just pure CO2. You see, there are so many other pollutants that those could alter the functioning of CO2. So there could be very, very serious effects. The other very important thing to know is that actually there is a golden opportunity, to mop up CO2 by plants, simply because at this point in time the photosynthesis will be more productive with the higher CO2 levels. But what have we done? We have done deforestation. So there are fewer trees. So trees could have taken up the CO2, but they're not there because of deforestation. Look at the irony of it. Okay, so we have made things very bad for ourselves, including with these land use changes, of continuously bribing people and converting agricultural land to urban land, and then just making skyscrapers and all kinds of things there, and then knocking off the forest. Every few days, and now it's less. I used to see fires burning in these mangrove areas, in Kharghar, this, that. And you see, a lot of burning activity. Okay, but today they are also because of natural causes, and forest fires have increased. Now, so the most wise thing, which every kid knows, okay, but somehow it's only when a paper is published in Nature then people take notice of it. What a stupid thing! Everybody knows that if I have more trees, then it will mop up more CO2. Okay. Now these people have done a calculation and said that if we can plant a trillion trees, trillion means 10 to the power 12 trees, when in fact the reality is every day the number of trees is going down, not up. Okay? Trillion trees means, suppose I take a population of 10 billion, which means about 10 to the power 8. Okay, we are talking about 100 trees, per person, per individual. Where is that? It's not there. There's nowhere near that many trees. Okay. Now, even if you were to plant today, I honestly don't know what's going to happen. If you plant, because what are we seeing every day? You go, you see how California is burning. Forest after forest, Australia. I mean, thousands and thousands of hectares of land is being burned. Even as we speak, there are wildfires, continuously burning things up. Why is it happening? Because our atmosphere is heated up. Okay, and so the possibility of an accidental spark, and all it needs is a spark to light a fire. And once the thing starts burning, you can't stop it. Okay, and so today one will have to look very, very carefully at this strategy of planting more and more trees. And because there could be a calamity as well, that if those trees start burning because of forest fires. And it is happening because of climate change. So there is a much higher temperature today, and at these high temperatures, things can catch fire. Okay? And also deliberate anthropogenic ignitions. People actually make things burn. Okay? You've seen, for example, Haryana and all, wherever after their harvesting season, what do? They take all that stuff, and light a match. Okay, and that whole thing is spewing out smoke, and Delhi is crying, because all that smoke is drifting towards Delhi, okay, and when in fact, if you were smart enough, we could have baled all that, okay, we could have converted it into very nice compact biofuel and used it instead of coal in our power plants. That would have been such a wise thing to do. You're still burning, but you are now burning instead of burning coal, and keeping it fixed. Okay, so these are the issues, but certainly I think planting more trees is the one thing that you need to look out for. And let me also tell you that all of you, what I want you to do, and later I'll show you, is that which has more area, or land or our oceans?
Oceans.
Which covers more area?
Oceans.
Oceans, right. So, as our population is going up and land is becoming scarce, I think that we should look at the opportunity to grow alternative agriculture and things in the sea. You know, you may because all of us just look at terrestrial plants, but there is an opportunity to undertake massive cultivation over thousands of square kilometers in the sea, and that might actually mop up a lot of CO2. And the other advantage in the sea is that because it is in the sea, I don't have the fear of it catching fire. Okay, this is something that occurred to me as I was speaking to you just now. And so even from a safety point of view, it would be quite interesting to look at. Let me just put it. Otherwise, I'll forget. Cultivating in the sea would also have the advantage of eliminating the probability of accidental fires. Okay? So, what I want you to do is that when you're looking at renewable resources, biomass, etc., I want you to look at it with the totality of context. Not just, hey, I've made this and, from here I know how to make biodiesel, I know how to make this. I mean, those are all downstream. They are not the issues. Okay? The larger issue is biomass. Now, what we will do is that over the next few slides, we will look at that where all is there an opportunity to utilize carbon dioxide, and some of it will is quite practical, and we will look at that. Now, before I come to that, one of the areas we will look at is the use of carbon dioxide in the extraction of oil. Oil itself, which you're pumping out from the ground, can that benefit from the use of carbon dioxide? Okay. Now, this over here on the right is the phase diagram of carbon dioxide. Does everyone know a phase diagram? Or let's put it, does anyone know what is a phase diagram?
Yes, sir.
Okay. All right. So if you look at the phase diagram of carbon dioxide, okay, now this point is what is known as the triple point. What is the triple point? Where basically the solid, the liquid, and the gas coexist together, right? And this, in the case of carbon dioxide, um, uh, typically it will be around 0.6 megapascal, which will be about roughly about 6 bar. Okay, 1 bar is equal to 0.1 megapascal. So the bottom of this y-axis 0.1 is 1 atmosphere, right? Okay, 10 to the power 5 pascals is equal to 1 bar. Okay? So roughly we are talking about around 6 bar, not a very high pressure, okay? And also not a very high temperature. You know, you're talking about a temperature of what? About 220 Kelvin. Okay, so you know, you can work it out. You know, it's a very achievable kind of a temperature. You know, and this is where all the three can coexist. We normally don't see the liquid state of CO2. We know that ice can sublime, you know, or because we are normally looking at things in this particular pressure range. Okay, so here, of course, you can imagine that if you're close to the 1 atmosphere pressure, that when a solid will heat up, it will directly go into the gas phase, right? It will not go into the liquid phase at all. But if you could reach this point, you would actually see solid liquefying as well as a part of it existing in the form of a gaseous CO2. Okay. Now, if I start increasing the pressure more and more, and at the same time I start increasing the temperature, okay, I reach what is known as the critical point. Okay. This point, you can see 7.39 megapascal, so you're talking about around 74 bar. Okay, and in terms of the temperature, it's a it's a, like room temperature. You know? So if you were around room temperature and 74 bar, you know, you would hit the critical point of carbon dioxide. When I go beyond the critical point, so if I go further over here, you know, I reach what is known as the supercritical region, and over here, actually, you cannot differentiate between the densities of the liquid state and the gaseous state. You know, the two are the same. So effectively, you know, they will appear as if it is a single phase, simply because there is no density difference. Okay, but actually there is both liquid and solid, but or you can think of it just as a uniform single phase. Okay, and that is the supercritical phase. Okay, now this point in the supercritical phase, which is not that difficult to reach, okay, has been utilized, okay, for what is known as enhanced oil recovery. Okay, so let us try and understand what is enhanced oil recovery. Now, typically, this is your oil well. Okay, this is your, you know, your oil will be somewhere here. It's being pumped out. Okay, normally you'll have this production well, which is pumping out, you know, oil. All right. Now, what the supercritical CO2 does, okay, is that, you know, supercritical CO2 in this region is almost like a non-polar solvent. You know, it's like hexane. Okay. So you know, it has excellent solubility with your oil. Okay. Now, in this state, when you push a lot of this CO2 into the oil, which is normally quite viscous, becomes extremely fluid. Okay, its viscosity reduces drastically. Okay. And second, many times, you know, the viscous oil will not get released from the solids in which it is trapped. But when this supercritical CO2 is being pushed in, and it is becoming very fluid, in some ways, sometimes like almost a gas, it can enter into every nook and cranny, of the oil strata, and it can push out, all that oil which otherwise would be very difficult to get out. Okay, so all of this comes out, and you can increase the production of oil by something like maybe about 10% or thereabouts, through the pushing of CO2. So CO2 today is being looked at very, very actively for this purpose, okay, and which is basically enhanced oil recovery. Now here the problem is that when this thing comes out from here, it is what? What will come out? The oil will come out along with dissolved CO2, because CO2 dissolves very well in oil. Then after that, you will take out the CO2. Obviously, when the temperature increases and the pressure is released, again the CO2 will escape as a gaseous CO2. Okay, and then that CO2 is once again compressed, and put. So in this, there is only a limited amount of CO2, which you can actually consume in the process, because it comes back. Okay? But people are also looking at that. Suppose you have seen the phase diagram, okay, and what are the regions, for of pressure, etc. It could well be that when the oil is coming out, I might be able to substitute a part of these spaces that are created because of the oil getting out with CO2, which can be kept in a liquid or a solid state. So in which case, I might be able to sequester very large amounts of CO2 underground. So this could be very interesting. Only thing is that you need to understand that there is a huge penalty, in terms of the energy that you require, to pressurize CO2 to the supercritical point, and then to leave it over there. Obviously there is a large energy input, but many times what happens is in oil wells, there is a lot of wasted fuel, which is all getting burnt and things like that. And so that energy could actually be utilized in carrying out some of this pressurization of CO2. Okay. The other thing is, just to show you that it is not just CO2. You can actually play this game with even natural gas. Like if I take natural gas and inject it into the oil well, I can actually enhance the recovery. That's been done. I could even take flue gas. Okay, what is flue gas? Flue gas is effectively just the burnt stuff, which will not be pure CO2, but it will have about 10 to 12% of carbon dioxide. The rest will be moisture. Then there will be SOx, NOx from the burning process, and there will be a lot of nitrogen because you're pushing in air to burn carbon and make CO2. So the oxygen gets consumed, but the nitrogen remains. So you have something like 80-85% of nitrogen, which is still left in flue gas. Now, what happens is that because the amount of CO2 in the flue gas is very limited, just about 12%. So to pressurize it, to the high pressures means that because the nitrogen will be of no use, but I have to pressurize it. You know, so there will be a lot of wastage of energy in unnecessarily pressurizing also the nitrogen and other things. You know, and secondly, flue gas has many other contaminants, and those could have an adverse effect on the oil. You know, and so while there was work taking place, you know, on the use of flue gas, but effectively after about 1994, you know, or thereabouts, mid 90s, you know, the use of direct flue gas was stopped. And instead, what people started doing is purifying the flue gas and getting pure, relatively pure, something like maybe 90-95% of CO2, and then using that, you know, for the enhanced oil recovery. And so you can see that you know, this has really taken off. Okay? But this is not the only way in which you can have enhanced oil recovery. As I told you, you can use natural gas, you know, so that's quite a way. The nitrogen injection. So to that extent, you know, the flue gas would be serving both purposes because it has also got nitrogen, you know. But people have also tried to put pure nitrogen, you know, and try to increase the recovery. There are also chemical and thermal methods, you know, to enhance the recovery of oil. For example, you can add some chemicals, you know, into along with steam into the oil wells, and what these chemicals do is that they lower the surface tension. And once you lower the surface tension, then the oils, you know, get dissociated from the substrates in which they get stuck, you know, and it comes out more readily with water. So that's one thing. Or you could directly, and this is being practiced, and in fact this is the bulk of the work, where you inject high temperature steam, you know, very high temperature steam, and so it heats up the oil and it makes it less viscous. So ultimately, in both cases, you are reducing the viscosity. You know, here you are doing it by injecting supercritical CO2, you know, and here you are doing it by basically heating up the oil using steam. You know. And so these are all the ways of really enhancing the recovery. But keep this in mind that the use of CO2, you can see that today it is almost equal to that of the thermal processes. You know, so it is really expanding. You know, the growth of use of CO2. You know, for enhanced oil recovery. And if some of this CO2 can also be stored in the reservoirs, you know, nothing like it. It would have been very good. Okay. Okay. Now let's take some other quite ingenious work, you know, which has been done on use of CO2. Okay. In fact, this particular work was got the U.S. presidential medal, you know, and you can see in your area, green chemistry, green tech challenge. Styrofoam is nothing but a foam polystyrene. Okay, so you have seen those cups now in which you get coffee and things like that to drink sometimes, you know, and they're very good insulators. Okay, and very light. Okay, and the insulation property comes really from it having very large amount of air, you know, or some foam in that polymer, and that is also what makes it so light, because the percentage of plastic, the polystyrene in the cup, is very low. It is primarily air, which is entrapped in the plastic. Now, earlier, you know, when they used to make styrofoam, the foaming used to be done by CFCs. CFCs, as you know, are chlorofluorocarbons. Very bad for the ozone layer, and they are being phased out. Okay, but this is what was being used. Okay, to actually make the styrofoam material. So now what these people did in Dow, okay, is that they developed a technology by which they could substitute these CFCs with carbon dioxide. In other words, they were able to make carbon dioxide as the foaming agent in place of CFCs. And there was no compromise in the quality of the styrofoam sheets. Okay, they were very good. They were moisture resistant. They were recyclable. Nothing was lost. Okay, and these things are used. For example, all these eggs, are kept in these packages which are made of styrofoam. Okay, and they are shaped, and you put one egg in each of those holes. Okay, and so egg cartons, fast food containers, everything. They were able to replace the use of CFC. Now, this was a huge impact, okay, and that's the reason why they won the presidential medal. Because on the one hand, they knocked off the use of CFCs, which is so bad for the ozone layer. Okay, and on the other hand, they were able to mop up the CO2, which they were probably producing in their factories. Okay? So they gained both ways, and it was such a good technology, and they realized that many people will want to avail of this technology. So they're now even offering this technology on a licensing basis to people. I mean, you can buy it from Dow. Okay, and so this is one of the very wonderful uses of CO2. And you can see where 1996, 25 years ago, okay, they did this work. They did the work probably 30 years ago. 25 years ago they got the prize. Now, there is, just to show you that there is a huge amount of interest in technologies to capture carbon dioxide. Okay? And that's all because of what I told you, the global warming and CO2 being 411 ppm today. So this, for example, you can see there were these 6 projects were selected by the US Department of Energy as very promising potential technologies for capturing CO2. I don't think all of them are that good. None of them actually are of the class, of this. For example, this is so easy for anyone to understand, how it benefits. Okay, but broadly I divided, into certain areas. One is that we have seen that the oceans, what do they do? That the CO2 is ultimately taken, becomes carbonate, bicarbonate, and finally at some point, over long years of time, it becomes calcium carbonate, limestone. Okay, there will be a huge effect of pressure and temperature and things like that on that whole process. Okay, so people are looking at ways of similarly, but by sort of man-made or human efforts, trying to see if they can convert the CO2 back into carbonates. So 2 of the projects are basically focused on carbonates. This one and this one. Okay. Then there is a technology which is pretty smart. I will say as smart as this, where people are taking carbon dioxide and reacting it, with monomers to form polycarbonates. You know that polycarbonates are very, very important thermoplastic polymers. Okay, and it goes into all kinds of applications. Polycarbonates, you can look it up. Okay, so this company Novomer, and I believe another company somewhere. Okay, they are basically looking at trying to make polycarbonates. Okay, which would be nice because you can mop up a lot of CO2 in the process. There's a third, okay, which was talked about a lot at one time. It's talked about less today, okay, which is that to use carbon dioxide, in flue gas to actually make biofuel. Okay? And the idea was that you can, there are algae, photosynthetic algae, which can trap this CO2 and effectively it forms quite a bit of oil, which is stored in the algae, and then you extract that oil and then you can use it as a biofuel. Maybe at some point when we are discussing biofuel, I'll talk about some of the work that was done in India itself, which was quite pioneering, at that time. Okay, but the problem is that it requires very large area, large amount of land, because where will you grow this algae? People were constructing pans, etc. Massive pans. Okay? But it's not practical to sequester more than maybe about 6 to 8% of the CO2 in flue gas. The land requirement is just too huge, and so and then there are downstream complexities and things like that. But anyway, just to tell you that this is another area which had captured the imagination, which is to utilize flue gas, the CO2 there, and to produce biofuel. Okay. All right. Now let me tell you about some other fairly smart ways of sequestering CO2. Okay. Now you can see this is an interesting article, and it says recycling CO2. Okay, and one of these technologies is related to production of sodium bicarbonate. Okay, baking powder. Now, all of you have heard of the Solvay process? Has everyone heard of the Solvay process?
Yes, sir.
Yes, sir.
Okay. Right. So this is the net chemistry of the Solvay process. Okay. Effectively, what you're doing is taking sodium chloride, taking calcium carbonate, converting it into sodium carbonate, which is soda ash, and it forms calcium chloride, which is a byproduct, effluent. Okay, calcium chloride. Now, this process is thermodynamically not favorable. Okay? You can see delta G is plus 60 kilojoule per mole. So you cannot do this process directly. Right? But what Solvay and people before Solvay, in fact, it was really discovered by a physicist, not by a chemist, is an indirect way to make this. Okay, and that is what you do is first you take limestone, you calcine it, you get calcium oxide plus carbon dioxide. Okay, now this carbon dioxide, because carbon dioxide is an acidic oxide, okay, the carbon dioxide reacts with ammonia, okay, and it forms ammonium bicarbonate, okay, NH4 HCO3, and you along with that you dissolve sodium chloride, okay, this is that sodium chloride. Now what happens is that when you do that and you get the temperature of the reaction etc. right, I'm not going into all the nuances, okay, uh, there is a sort of decomposition reaction, double decomposition, and so the sodium picks up the bicarbonate, okay, formed from ammonia and CO2, and it forms sodium bicarbonate, okay, and sodium bicarbonate, and what else will it form? It will form ammonium chloride. The ammonium bicarbonate, that ammonium part plus the chloride from the sodium chloride, it forms ammonium chloride. Ammonium chloride is very soluble in water, it remains in water, whereas sodium bicarbonate has a relatively low solubility and it precipitates out. Okay, so you can isolate the sodium bicarbonate. Then what you do is that you heat the sodium bicarbonate, okay, and it gets converted into sodium carbonate, okay, releases CO2 and H2O. Okay, this is the process, and then this CO2 is utilized subsequently in the whole process, and this lime which you got, you know, from here, this lime reacts with ammonium chloride and releases ammonia back, okay. So ammonia is like a catalyst, it's not getting consumed and it forms calcium chloride. Okay, so that's basically the sum and substance of this process. Now, what those people, you know, that article is about is that they have not made sodium carbonate, but they have effectively made sodium bicarbonate, you know, which is this. Okay. Now, just like I wrote this reaction, can you write a reaction between sodium chloride and calcium carbonate to make sodium bicarbonate?
Sir, can you repeat the question?
No, I'm just asking, just like I wrote an equation, sodium chloride plus calcium carbonate going to sodium carbonate plus calcium chloride. I'm just asking you that if I form sodium bicarbonate instead of sodium carbonate, okay, I'm just asking you to write the equation for that. So what happens is that I write 2NaCl plus CaCO3 plus CO2 plus H2O goes to 2NaHCO3 plus CaCl2. Now, what I did not tell you, I thought you might pick up the clue. When I heat sodium bicarbonate and it forms sodium carbonate and releases the CO2, this is the CO2 that goes back into this reaction. That's how I'm able to get all of the CO2 utilized. You know. But if I only make sodium bicarbonate, you know, I don't have sufficient amount of carbon. Okay. So what has been done is that the second carbon, one carbon is coming from the calcium carbonate, basically the CO2 from calcium carbonate. The second carbon dioxide is coming from flue gas. Okay. And now if I balance this equation, I can write it as 2NaHCO3 plus CaCl2. I don't straight away get this. I'll first, as I told you, get bicarbonate, and then the ammonium chloride is decomposed with lime to make release back ammonia and calcium chloride. Okay. So effectively, there is a huge opportunity to capture quite a bit of carbon dioxide, you know, by reacting it with ammonia, you know, to form ammonium bicarbonate. Okay, and so that's what those people have done, and there's a huge opportunity. I mean, you know, and you could actually make a lot of money because you can sell carbon credit, you know, and that fetches quite a bit of money. Okay? Of course, this is nothing new. like for example, this patent, okay, which was granted in 2009, right, effectively talks about reacting flue gas with ammonia to form ammonium bicarbonate. And then it's a simple question of taking this and reacting with sodium chloride and basically forming sodium bicarbonate and ammonium chloride. And what you can also do is that ammonium chloride can is a very good fertilizer. So I can actually isolate the ammonium chloride after taking out the sodium bicarbonate, and then I can completely eliminate the requirement of calcium carbonate. You don't need limestone. Okay, all I need is ammonia and flue gas and sodium chloride. Okay, and so this is the kind of innovations which can really lead to very large impact on the environment. Okay, and you should always look out for where you can apply innovations, where can you do these clever things which make a huge impact. Okay, is that clear to everyone?
Yes, sir.
Yes,
Okay.
sir.
All right, let's take another case, and I'm deliberately taking cases that you are familiar with. Okay, I'm not taking things which are totally esoteric. Okay, all of you have heard of the Haber process,
Yes, sir.
Yes, sir.
right? And also heard of the Haber-Bosch process,
Yes, sir.
right? Okay. Now, what is the Haber-Bosch process? Uh, of course, if I ask you, what is it? What does it do?
Producing ammonia.
From
H2 and natural gas. H2
H2
And two,
and
N2.
N2.
And where does the H2 and N2 come from?
atmosphere.
Atmosphere.
And
No, sir. From natural gas, I guess.
Yes. Okay. So this is the process. Okay, where first you clean up the natural gas, you remove impurities. You take natural gas, right, and then carry out what is known as primary reforming by cooking it up with steam. Okay? It generates hydrogen and carbon dioxide and carbon monoxide. Okay, then what you do is that you push in air, into this mixture, okay, and along with some amount of more of the natural gas, okay, and ultimately what you'll do is that you will consume all the oxygen in the air, by burning it with methane, and it will form more amounts of hydrogen, and there will be nothing left of the oxygen, and so all the air has effectively become transformed into just nitrogen. You understood? Okay. So because I have consumed all the air in combustion, so effectively after that you do some more things, and finally what you end up with is carbon dioxide, hydrogen, and the nitrogen from air. They've not written the nitrogen, but nitrogen. Okay. So these are the three things that you have. Then what one does is, by a very clever process, one separates out the carbon dioxide. Okay, using one of these amines, organic amines like diethanolamine. Okay, which is an alkane, basic, and carbon dioxide is acidic. So it binds to the amine, and I can separate it out, and I'm just left with then hydrogen and nitrogen. And that hydrogen and nitrogen is what finally is what you are consuming in producing ammonia. So it really did, the hydrogen and nitrogen really came from natural gas, steam, and air. So that's the reaction. Finally, once you get this and everything else is removed, you get ammonia. Now look at the brilliance that people realize that yes, fine, I'm getting hydrogen, I'm getting nitrogen, but what about this carbon dioxide? What will I do with this? Okay. It was separated out, but people were looking at an opportunity to use it. Otherwise, it would have just gone into the atmosphere. And then people realize that wonderful, you can react ammonia with carbon dioxide and form urea. And so what you apply in the field is not ammonia, you apply urea in the field. Okay, urea is the fertilizer. And look at the wonderful way in which the carbon dioxide was fixed. And look at the advantages. This ammonia is a gaseous substance. How can I apply it in the field? Ammonia is alkaline. It will spoil my soil. I can't apply ammonia. But when I react it and people realize that carbon dioxide is acidic. So finally, when I made urea and water, this urea is completely neutral. It's a solid. I can just spread it on the field. I can hold it in my hand. Okay. So you can see how cleverly, people used carbon dioxide. Okay. So every bit of the natural gas was finally ended up in my final product, which is urea. Okay. So this is the kind of and can you imagine the consumption of urea in the world? It's massive. Maybe something like what, 200-300 million tons. So so you are talking about fixing something like what, about 0.1 to 0.2 billion tons, okay, of carbon dioxide in this manner. Okay, so it's just phenomenal. All clear?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
So what we will do is that I'll just take 2 more minutes because time is up, I realized. Okay, just take 2 more minutes and then we'll close. Now we have discussed the urgencies. Okay, one urgency is that there is simply no fuel that is available, and in 50 years' time, the situation is going to get pathetic. Okay, so it is not just because you're a nice guy that you are focused on renewable energy, because otherwise you will have no source of energy. And the second, because of the burning of fossil fuel and the carbon dioxide, and you have seen how it is increasing in the atmosphere, and the chaos and the havoc that it's causing, India being the most polluted city in the world. Okay, and so there is a real urgency in finding alternatives, and that's why renewable energy is so important. Now let me ask you, what is renewable energy?
The energy collected from the natural resources.
Energy collected from the natural source. Okay. Could you build on it a bit uh, and draw on the word renewable? I mean, then I could have just called it natural energy, right?
Which can be reused.
Which the energy can be reused.
Source can be reused.
The source can be reused, or what you want to say is that it is an infinite source, right?
Yes, sir. There is
Yes,
no
sir.
limitation to the
No
source.
limit.
Or it's a never-ending source, right?
Yes,
Like
sir.
the sun is a never-ending source. I mean, yes, after maybe 100 billion years, it might go bust, you know. But we are not talking about those time frames. And in any case, when the sun goes, the earth goes, we all go, problem ends there, you know. But so long as we are there, you know, the sun is there, and so it's a never-ending source. And just like Herschel said, if the sun's energy is never-ending, wind energy is never-ending, solar energy is never-ending, geothermal energy is never-ending, right?
Yes, sir.
Okay, but coal energy is ending because it takes millions of years to produce. Okay, so you know, of course, constantly some coal is being made, you know, but the rate at which we are depleting the resource is much higher than the rate of formation. Okay, correct? So let us put never-ending source rate. Now, what is important is rate of consumption must be less than
Rate of
or equal to rate of generation. Right? If coal was being generated at the same rate as I am consuming, or if oil was being generated at the same rate as I am consuming, no issue. It would have been a renewable source. But we are consuming those at a much faster rate than the rate at which they are being formed. Okay? And that is why those are non-renewable. But otherwise, remember, they are natural sources. Oil, coal are all natural sources. Correct?
yes, sir.
There's nothing
Yes, sir.
unnatural about them. Okay. But we are talking about a never-ending source, and rate of consumption must be less than or equal to rate of generation. Okay?
Yes, sir.
Correct?
Correct, sir.
And so this one, I'll just put a question mark. And I've just tried to put, you know, some definitions like never-ending source you can replace by sustainable source. You understood? Okay. The second is that you know, a form of energy where like look at the beauty. I'm burning, I'm getting CO2, I'm capturing CO2, and I'm getting trees back. Okay, and from which I can get biomass and energy back. You know? So we can also put uh, allows in some cases to have a closed loop. Okay? If the rate of burning of the fuel was the same rate at which photosynthesis takes place, no issue. That's great. Okay? So, you know, never-ending source, we can call it sustainable source. All right? Okay. Now, what we will do is that we will stop here today. Okay? And yeah, we'll stop here today, and we will continue next week. Okay? Now we are almost through with our introductory parts. Okay? So from next lecture, we will go one by one into each of the sources of renewable energy. We will just sharpen the definition a bit more. Okay? And then maybe I'll stop it here. Okay, and then we will go one by one into each of these and deal with them in more detail.